I'll try to live up to the expectations in the talk. So I'll talk about meta-learning and self-play, which are two topics which I think are interesting and exciting and worth talking about. But before I dive into the technicalities, I want to give you a little bit of an overview about why neural networks actually work. I don't know for sure how much background everyone has in machine learning. I assume some, but I also think there's some chance not everyone is absolutely fully familiar with everything. And so this, I think, is the most, in some ways, the most important slide. This is why deep learning works. And so it's not obvious that deep learning should work. And so if you want to, so what's really happening is the following. If you want to solve the generalization problem completely, it's actually possible to prove mathematically that all you need to do is to find the shortest program that explains your data. And that's something you can prove. And the proof is easy. It's just not well known. And if you're interested, I could tell you about it offline after the talk. But the point is, intuitively, it just makes so much sense. If you can find the shortest program that explains all your data, then you can generalize as well as you want. The short program can just take all the regularity out of the data and put it into the short program. Now, we don't do this because we cannot find the shortest program which explains the data. But if we could, it'd be great. It's not computable. That's one of the reasons why we don't do it. But we can't do short programs, but maybe we can do small circuits. And that's what deep learning is all about. It turns out, through a great fortune, which we currently cannot explain really well, that we are able to find the best small circuit that explains the data. And so that's what a neural network is. A neural network is a kind of circuit. And so, wrong direction. And the backpropagation algorithm can find a circuit, the best circuit, and that's it. So short programs are the best thing ever. If you could have it, you would have massive, overwhelming generalization. That cannot be done. But circuits are kind of close. You can build a computer out of circuits. If you have many layers of circuits, you can compute all kinds of functions. And it turns out if you can solve the circuit search problem. Like, in fact, this is why I believe that the backpropagation algorithm is so fundamental, because it solves this fundamental problem. And it solves it. This problem is basically solved for all practical purposes. And so that's why I think that this is why it's going to stay with us until the very end. And so what's really going on is that we can think of training a neural network as solving a neural equation. You've got your parameters. They have all these different degrees of freedom. And every training case introduces a small constraint. And now you just can imagine the entropy flowing from the training data into the parameters, eventually reducing the degrees of freedom of the parameters. But the crux, the reason why deep learning works, the reason that the community now has the audacity to talk about AI, which was not the case before, is that we have this one algorithm, which is called the backpropagation, which was invented by Jeff, which can just find the best circuit But the point is, the problem of finding the best circuit is solved. And if you could find the best short program, you could really solve generalization in a way that cannot be improved upon. But we can't do that. So we're going to do the next best thing, which is find the best small circuit. And that's what deep learning is. You just have your training data, and you just let the information flow from the training data into the parameters. And the means of this information flow is the backpropagation algorithm. And it just works again and again and again on every problem without exception, because it doesn't care what problem to solve. And I think that's the most amazing thing. That's why people care about deep learning at all, even to the slightest bit. Now I want to talk a little bit about reinforcement learning as well. So reinforcement learning has two properties which make it interesting. So the first property of reinforcement learning is that you have, as a framework, it's a pretty good framework. You have a framework where you have a stochastic, uncertain, unknown environment, which can be whatever you want, more or less. And you have an agent which is trying to achieve goals in this environment. And yeah, it's a great framework. But what's more interesting is that fairly good reinforcement learning algorithms exist. That's the interesting part. It's not just the framework. The framework is cool. But it's the reinforcement learning algorithm that can actually solve problems. That's what makes it really cool. And that also means that if you're going to improve your reinforcement learning algorithm and make it extremely good, then you'll be able to achieve a system which is truly powerful, that can achieve really complicated goals in the real world. But that's basically, okay, the laser doesn't work. It's because good reinforcement learning algorithms exist. They are good in a sense that they can do useful things, but they are nowhere near as good as they could be. So, like, one thing I don't really know is kind of what's the state of knowledge of the crowd. So please raise your hand if you are very familiar with reinforcement learning. Okay, so actually, please raise your hand if you're very familiar with deep learning. Yeah. So I'm going to spend a little bit more time on the context setting. So basically, oh, there's also a whiteboard. I might use that. But basically, you just say, hey, I've got this beautiful diagram which says I have this agent and I send some actions and I get my observations and rewards. And the environment is stochastic and big and complicated and it's given by the world. And my agent is a policy, and I can just run my agent and calculate its expected performance. And that's how good it is. So now I have an optimization problem, a mathematical optimization problem, find the best agent. That's the reinforcement learning problem. And so it's very clear that this is a very general framework, because it doesn't only deal with passive perception, it also deals with achieving goals. And you can have a very complicated goal that you specify somehow. You can specify how well you've done, and then you just run your agent a bunch of times, figure out the expected performance of the agent, and I try to solve the problem of maximizing this. Now, of course, the agent has to be a neural network, because what else is going to be? I mean, it's not. I mean, it's an objective statement of fact. There is no other substrate which can both represent lots of different things and which can be learned in this generic way. So yeah, your agent gets some observations, produces some actions, you can do it again, and you run it for a while, then you get your performance. And then you ask yourself, how should I change my connections to do better next time? And I'll give you the 100% of the intuition in reinforcement learning in two sentences. Here's what happens. You got your agent, and your agent actually has some stochasticity in its actions. So your actions are a little bit random. You run your agents with the random actions. They're not totally random, they're a little bit random. And you get some performance. And if your performance is better than what you expected, you say, this was great. I want to do more of that again. These are great actions. Increase their probability. This is the core of reinforcement learning. It's not as advanced as it could be. It's still pretty unsophisticated right now. And basically all it says is, do something random, do something you did not predict, you don't really know what the consequence of it will be, and then see if you like the result. And if you like the result, treat it as training data. So that's a really simple idea, and it can be formalized in a variety of ways. So the most direct formalization of the idea of this direct idea of reinforcement learning, we just try something randomly, and if it does better than average, do more of that. That's the policy gradients. So you got your cost function, which is this thing. This is a cost function which tells us how well our agent is doing. You run your agent in the world, and then you get a score. Your agent got 3 points of goodness. You run it in the world again, you got 2.5 points of goodness. And every time it runs with slightly different actions. There is randomness. You take an action, you see the consequence. And then if things turn out better than expected, you say, this is great. My neural network should learn to produce more of this kind of output in these circumstances. Oh. Yeah. So if you take the cost function and you go through the trouble of differentiating it, you're going to get the likelihood ratio policy gradients. You're going to get the policy gradients. And there is some math, but we don't really need to look into that. It really truly boils down to, okay, who have seen maximum likelihood? Okay. So it's like maximum likelihood on your actions, were the good actions, the actions that lead to success at big weight. And that's all there is to it. And it turns out that if you scale it up a lot, it works pretty well. There's also a different approach, which is called Q-learning. And the reason I'm mentioning it here, it's a little bit more complicated than the, yeah, it's a little bit more complicated than the previous, than the policy gradient. It's a bit harder to understand. But it has one advantage that's actually important for some of the work I'll tell you about later. It is off policy. So policy gradients, you run some experience, and then you see, okay, given my experience, what do I need to do to improve? But Q-learning, you can also learn from the experience of someone who is not you. You can learn from someone else's policy. It's like, let's say you're really good at, let's say you want to learn to ride a bike, and you are okay at riding a bike, and then you see someone who is worse than you who is riding a bike, you can still learn from their experience. This is what Q-learning lets you do. It lets you learn from the experience of policies other than yourself. And it's going to be important for a mildly technical reason in the future. So if you found this a little bit confusing, don't worry about it. It's just a technicality. But anyway, the conclusion is that reinforcement learning algorithms exist, and they're pretty good. Let us continue to the next slide. Oh, this previous slide now. Okay, so I will actually give you just a brief explanation of what Q-learning is. Now I'll explain to you what the Q function is. So the Q function is basically the answer to the question of, if I do something, how good it is. That's what it is. If I'm in a certain state, I take a certain action, how good do I think it's going to be? That's the value. That's what the Q function is. So for a given state and a given action, that's a transition, I'm going to get some future. And this future in this rectangle, that's the Q function for this state and this action. So I would say that this is meant to be like, yeah, so hopefully this clarifies what the Q function is. If it doesn't, wouldn't worry too much about it. Just one more thing here. The Q function is recursive, because then if you get to state S prime and you take action A prime, you have this, like this inner rectangle is the Q function of S prime and A prime. So you have this recursivity to the Q function, because it just tells you, if I'm here and I take an action, how good is it going to be? Well, okay, I took one step. Now I can just basically repeat this whole argument all over again. So the Q function is recursive, and you can estimate it recursively with the Bellman equation. And so, like, if you find this kind of stuff interesting, and you find yourself not being able to understand all the details completely from my presentation, just read up on it. It's really, the amount of depth here is very limited. And so I think it's going to be worth the effort. So yeah, the real potential here is that you could build a really good reinforcement learning algorithm, improve it in a variety of ways. And once we do so, perhaps you could make the statement that the purpose of our field will be achieved. I think this is, this is not a 100% accepted statement by everyone, but it's definitely a lot of truth to that. If you have a truly, really great reinforcement learning algorithm, then you can achieve whatever, you could use it, actually plug it in where the environment is going to be the real world, and see what it's going to do. Okay, next I want to start talking about meta-learning. So meta-learning is this cool idea that you learn to learn, where you say, okay, well, we don't know what a good learning algorithm is. We are just human researchers. What do we know? Maybe we will use our bad learning algorithms to learn good learning algorithms. This is the idea of meta-learning, that you can somehow learn to learn. And it has a fairly, the idea of meta-learning is still in the promising stage. But it's pretty cool, and you can already do a fair bit of it. And so I want to start by just telling you like how to think about it. I think we can see from our own experience that as we grow up and mature and gain experience, our ability to solve new problems increases. We acquire strategies and we acquire knowledge. And so it would be nice if we had systems which had some of that element as well. And so that's what meta-learning is trying to capture. So one of the most popular and simplest approaches to meta-learning is to reduce meta-learning to supervised learning. By the way, who knows what supervised learning is? And who knows that supervised learning on a really big computer and a big data set can solve any problem? Oh. It's true though. Well, supervised, whether you can solve any problem or most of them, it is definitely true that if you have a large training set and a large neural net, then you can solve a lot of problems. Supervised learning is unquestionably very powerful. So meta-learning says, okay, well, can we take some of this power and instead of use it to solve a problem, we will try to use it to learn to learn. So the idea is we will reduce meta-learning to supervised learning and later to reinforcement learning by saying, well, we will treat each training task as a training case. And so the way it looks like, you have an architecture which kind of looks like this. You have a neural net, which is your meta-learner now, and you give it as input all your input-output examples of the task plus the test case, and the output is the prediction. So you take your good old neural net, maybe sprinkle it with some of the more recent innovations like attention, and now you can give it all the information about the task plus the test case, and that thing meta-learns. And I want to tell you about two success stories of this approach. So one of the success stories is the Omni dataset. I believe it was introduced by Josh Tenenbaum's lab. I don't know the first paper when it was introduced. I know that it's definitely been used in this paper by Brendan Lake, which made it to Science. Where basically they've designed these different characters. And this figure is from that paper, by the way. So they designed these different characters. They had I believe they had 1,000 different characters, and they had 10 examples of each character. Or maybe 10,000 different characters, but something of this order. 1,600 different characters and 10 examples of each character. Yeah, thank you. And so this data set was designed to show that deep learning is limited. But it turns out that if you simply say, okay, I'm going to use this approach to learn to solve this kind of task quickly, then it just works. And you get basically superhuman level performance. The best results by Mishra et al., they get 98% on one-shot 20-way classification. So you give it one example of the class, and you give it a test case, one of 20, that belongs to 20 different classes, and it just needs to tell you that they belong to the same class or not. And if you formulate it in this way, then suddenly you can have very rapid learning. And it looks really promising, it looks really encouraging. But yeah, look, if you reformulate the task of learning to learn as a supervised learning task, or later as a reinforcement learning task, then we will see that actually you can learn quickly. You can train a neural network. Basically, the neural network becomes the learning algorithm. The learning algorithm is now here in all the connections. So that's really cool. Another success story, which has a different flavor, but it also fits under the learning to learn umbrella, is the neural architecture search by Zopp and Barrett, Zopp, and Kwok-Lee, where they just say, we have one task. We just want to find the best possible architecture, neural net architecture for this task. Can we do that by just searching really hard with hill climbing? And it turns out that it works pretty well. And one really great thing about doing things like architecture search is that an architecture takes a very small number of bits to specify. And because of that, it can generalize. Things that have small number of bits to specify have a chance to generalize, while things that have a lot of bits have less chance to generalize. So this is another success story of meta-learning. But meta-learning is still a promising idea. Like, for example, you go here and you say, look at this. Look at how quickly it learns to recognize the characters from a new class really quickly. Maybe we could use it to solve many other things. But it turned out to be not so easy. So now that I've set the context, I want to actually talk about some of the work that we've done at OpenAI on meta-learning. This is one paper called Hindsight Experience Replay. It was done by Marcin Andrichovich and lots of other collaborators. And the goal here is to try and address the problem in reinforcement learning. So one problem in reinforcement learning is exploration. If your reward, so keep in mind, remember how your reinforcement learning agent actually works. You receive your rewards, you take your actions, and at first they're pretty bad random actions. You receive your rewards. So your reward needs to be well designed for the agent to succeed, because it's not very smart at first. And if it gets no reward, it's not going to learn. So you need to do something. Maybe you can modify the reward to make it dense and make it easy to work with. Or maybe you could give it some expert demonstrations. I mean, these are all good ideas. But I want to present to you another idea, which I think is really cool. Like, the idea is spiritually correct. So let's change the problem formulation a little bit. Instead of saying that you want to maximize a reward, instead, let's say that you want to reach a state. You want to reach a state in your system. And let's say you attempt, so here is the diagram. Let's say you tell your policy, hey policy, can you please reach state A? It will not succeed. It will reach state B instead. Well, we can interpret the situation in one of two ways. One interpretation that this is an unsuccessful example to reach state A, but it's also a successful example of reaching state B. So we can use this failure to teach the system to perform something else, to reach state B. It's really simple. Anytime you do something, even if you don't succeed to do the thing you intended to do, you succeed in doing the thing you ended up doing. That's true. So you could use that for learning. And so, can you design a reinforcement learning algorithm around it? You definitely can. But it has to be a Q-learning-based algorithm, because the algorithm is of policy. When you try to reach A, this is on policy data for A. This is your policy trying to reach A. But this is not the behavior of a policy which tries to reach B. If you were to try to reach B, the policy would do something else. So you need an off-policy algorithm in order to be able to benefit from this data. This is why the Q-learning-like algorithm is important. And so, since we tried it on robotics, on simulated robotics tasks, we've used the DDPG algorithm, which is a continuous version of Q-learning. And I just want to show you the results because they're cool. Let's see the video. Now, I want to say that an important caveat here is that in this example, we are being a little bit unfair to DDPG because we use a very sparse reward. You get a reward only if you are within some epsilon distance of the final target. But under these regimes, it works really well. So I think, so if you look to the left, you'll see that DDPG will very quickly, sorry, the DDPG is on the right. It's not getting the reward, and it's basically going to give up. Whereas on the left, you have DDPG and her, and it just pushes the block in this very dynamic and cool-looking way. So that's nice. There'll be more tasks. Now it needs to push this green air hockey puck towards the goal. And it just has this, so in this regime, where the reward is really sparse, it has an overwhelming advantage over DDPG. Now, one thing I should say is that we found that these kind of tasks were pretty hard to do, even when you try to shape the reward as much as possible. In fact, the reason we came up with this algorithm was because we tried to solve these tasks that we showed you by shaping the reward, and we found that it wasn't very satisfactory. Yes?
Just a question about under what conditions of the action space and state space can you sort of say that this algorithm succeeds? For example, I mean, these were all motion planning, so maybe the state space.
Sorry?
Most of these algorithms were motivated by motion planning, right? Where you have like maybe the action space is maybe small three-dimensional vectors, and maybe the state space is, let's say, a set of oppositions or something. So these are relatively low-dimensional spaces. Like, what if your action space was, n-dimensional, or n is like 200?
Yeah, so we've had success with this on 200-dimensional action spaces and state spaces. There's no problem with action space. It's really the state space which poses a problem. I don't think it will work on a million-dimensional state, although it's one of those things that you need to try really hard before you can conclude that it's not going to work. Because if you run it with a very large mini-batch, who knows what's going to happen? So anyway, that's the algorithm. Now, we did discover that when you take the more basic algorithms and you scale them up, then they overcome their deficiency and eventually can match the performance of this algorithm. But this one, the Hindsight experience replay, it's quite a bit more data efficient, and it works well when you in the small mini-batch regime as well. It doesn't require a very large mini-batch only. So anyway, this is what we have on the Hindsight experience replay algorithm. Let's see what's going on. Yeah. And so I think that in an important way, this algorithm is spiritually correct, because it makes use of a bigger fraction of the data that's given to it. In conventional reinforcement learning algorithms, if, let's say, you try something and you fail, then you don't learn much from it. This algorithm tries to avoid that. It tries to learn from the failures, because it simply reframes failure as a different kind of success. And so, like, what would be like the important next step to push it forward? That would be to learn state representations in high dimension. If your observations are extremely high dimensional, you get to see your video stream. What should be these goals? Where do they come from? So a good answer is needed there. Maybe it's going to be representation learning, maybe some other kind of auxiliary objective, but this is the bottleneck for this kind of algorithm. Okay, now I want to talk a little bit about sim to real with meta-learning. Change the topic a little bit, still staying on the topic of meta-learning.